Ladies and gentlemen, welcome back to Algebra. We are in Chapter 9, Section 2. We're talking about independent and dependent events. Chapter 9, if you remember, is talking about probability. So the probability of independent events is where the outcome of one doesn't affect the outcome of another. Okay, so both the probability of A and B both happening is where those circles overlap. We can say the probability of A and B happening is the same as the probability of A times the probability of B. So we looked at that example where we had a coin being tossed, right? We've got heads or tails and a number cube being rolled. So if we want the probability of heads and 3, okay, then we can have the probability of heads times the probability of selecting a 3, which is 1/2 for heads and times 1/6. So the probability of both of these events happening is 1/12. All right, so here's an example. As part of a board game, you need to spin the spinner, which is divided into equal parts. Find the probability that you get a 5 on your first spin and a number greater than 3 on your second spin. Now those are independent events because spinning 5 doesn't eliminate the 5, doesn't change how many numbers are on the board. So there's 1 5. There are a total of 8 spaces here. So 1 5 out of a total of 8 spaces. Okay, and then we will multiply that by a number greater than 3. So that cancels out 1, 2, and 3, leaves me with what? 4, 5, 6, 7, and 8, and that's 5 out of the 8. So the probability here is 5 out of 64. Remember, you can always change that by dividing. 5 divided by 64, that's approximately 0.078. So if we want that as a percentage, move that 2 places, multiply by 100, and we get about 7.8%. Okay, so 5 out of 64, or 7.8%, is that probability of both events happening. Now, a dependent event is where the outcome of one event affects the outcome of the other event. Okay, so we would write probability of A and B happening is the probability of A times the probability of B following A, or B after A. Another way to write that is put a little line down the middle. That means B after A. Okay, an example for that would be if you're drawing a marble from a bag without replacing it, right? So we had an example like you have 2 blue marbles and 3 red marbles. Okay, so if I were to find the probability of drawing 2 blue marbles, well, first the probability, so probability of 2 blue is the probability of drawing a blue, and then times the probability of drawing a blue after I've drawn a blue. Okay, so first time there are 2 out of 5. This is 2 out of 5. Times after I've drawn a blue. So if I take a blue out, now I have only 1 out of 4. So 1 out of 4, and that would give me 2 out of 20. And I can simplify that down. That's a probability of 1/10, or 10%. All right. So that is a dependent event. Here we have a bag that contains 20 $1 bills, 5 $100 bills, and you randomly draw a bill from the bag. Set it aside. Key information right here. That means you're not putting it back in. And then randomly draw another bill. Find the probability that both events A and B will occur. A, the first bill is 100. B, the second bill is 100. Okay, so probability of A and B. Now remember, it says set it aside. That means these are dependent events. So it's the probability of A times the probability of B after A. Okay, so probability of A and B happening, and B is probability of A, $21 bills and 5, that makes 25 total bills. Always find the total because our probability is the favorable out of the total. We have 5 out of the 25. That's on our first draw. Next, after we've taken a $100 bill out, now we have 4 left in there. And how many total bills are in there now? We now have 24. So it's 5 times 4, which is 20, over 25 times 24 is 600. Simplify that down to 1 over 30, or we could say it's approximately 0.033%, 0.033, or move that over, multiply by 100, about 3.3%. All right, that's the probability of both of those happening. You randomly select 3 cards from a standard deck of 52 playing cards. What's the probability that all 3 cards are hearts? When you replace, A, we replace, and B, do not replace. B, not replace. So, remember 52 cards, 4 suits, divide that by 4 makes 13. Out of the 52 is hearts. Now, if we're replacing them, then it's 13 out of 52 every time. 13 out of 52. If we're not replacing them, the first time we draw a heart, it's 13 out of 52. The second time, if we've drawn a heart, then there are only 12 left, and there are only 51 cards left. If we're not replacing and we drew 2 hearts, now there are only 11 left out of 50. Now this multiplies and then simplifies down to 1 out of 64, which is approximately 0.016 or 1.6%. This one multiplies to 11 over 850, and that's approximately 0.013 or 1.3%. So the odds are better if you replace, which makes sense because then you have 13 of the hearts in it every time, whereas here you have fewer every time. All right. Okay, here we have a table, and we are to find the probability that a defective part passes. So a defective part passes. All right, that's 3. We first always find the total. Okay, so the total, because remember it's always part, the favorable part to total. Okay, so add those together, then we get 39 total. So the probability A is 3 out of 39. Okay, and B, the probability that a non-defective part fails, again find the total, that's 461. So that's 11 out of 461. We can change these both to decimals and percentages. So this can be simplified down. Always simplify your fractions. That's 1 over 13. And that's approximately 7.7%. And this doesn't simplify. That's simplified and is approximately 2.4%. All right. At a school, 60% of students buy a school lunch. Only 10% of students buy lunch and dessert. What is the probability that a student who buys lunch also buys desserts? Again, there's multiple ways that you could approach this. Okay, here's one of them. Remember, if we want to find the probability of A and B, we said we have to take the probability of A happening and multiply that by the probability of B after A. Okay? Now, if I know the probability of A and B happening, which I do in this case, students buy lunch and dessert, okay, then I can divide both sides. If I divide both sides by P over A, right, then I get the probability of B after A. Okay, so the probability of B after A is the probability of students buying lunch. That's P, A, and B over the probability. That's buying lunch and dessert. This is just lunch. So P and B is 0.1, and this is 0.6, which is just 1/6. Right? We can always move the decimal as long as we're moving them both on top and on bottom. And that's approximately 0.167, and that is 16%. 16.7%, sorry. There we go. That's the probability that a student who buys lunch also buys dessert. There you have it, ladies and gentlemen. Good times. Check in again next time for another fun lesson.